In Module 6, we're going to be working a whole lot more with Newton's second law, just mainly because there are so many situations where Newton's second law applies. And the first part of this module talks about equilibrium, and specifically it's talking about translational equilibrium. And if something is in translational equilibrium, it just means that the sum of all of the forces acting on it is equal to 0. So if that's true, because we know that force equals the mass times the acceleration, if the sum of the forces equals 0, then the acceleration on that object is also going to be 0. Now, you can have two situations where your acceleration is 0. Either your object can be at rest or it can be at constant velocity. So I can take translational equilibrium and I can break it down into two other types of equilibrium. It can be at object is going to be at one or the other of these things. So it could be at static equilibrium, which means the object is going to be at rest, or it could be in dynamic equilibrium, which means that the object is going to be at constant velocity. So static and dynamic equilibriums are just two special cases of translational equilibrium. Now, the problems that we're working here are going to start to look pretty familiar simply because we've worked problems where we've had to break things down into their horizontal and vertical components before. And so we're going to be doing the same type of thing here. So the concept of how to work this problem isn't too much different from what we did a couple of modules ago, but actually solving it gets just a little bit more sticky just because of the algebra that's involved. I am going to work example 6.2 for you. Now, example 6.1 is worked very, very similarly. The difference between 6.1 and 6.2 is that in 6.1, the two angles that you're using are identical, and in 6.2, the two angles are different. So in example 6.2, it says a 5-kilogram flower pot is suspended from two strings as shown below. What is the tension in each string? Now, the first thing that you've got to be able to do when you're working problems like this is that you have to be able to draw a diagram. And as I've mentioned several times before, draw your diagram nice and big so that you can really put everything in there so you can really see clearly what's going on. So up here, I've got my flower pot drawn already. It's a 5-kilogram flower pot, and I've got it attached to the ceiling with two cords. Now, I have to say, if I was going to hang a flower pot from my ceiling, I would want both of those angles to be the same because I'd want it to be nice and even. And I can't figure out why someone would hang a flower pot with the strings at two different angles. But I didn't hang the flower pot, I'm just working the problem, right? Okay? So what we need to do is we need to analyze all of the forces that are acting on this flower pot. So this string is pulling upwards with a force in this direction, and so we're going to call this T1 because that's the tension in the string or in the cord. This cord is going to be pulling upward here, and so this is going to be T2. We'll call that one T2. And I know that those can't be the only forces acting on the flower pot because the flower pot's not moving. There has to be something that's balancing these forces. And so what other force is acting on it? Well, gravity's acting on it. So that means the downward force acting on it is going to be the weight. Now, we know that the weight is the same as the mass times the gravity. So that is going to be 5 kilograms times 9.8 meters per second squared. And so therefore my weight is going to be 49 newtons. So I'm just going to go ahead and have that in there so that I have that number available because I'm going to be using it anyway. All right, so the weight is acting straight down, but the tensions are acting at an angle, so that means that they're going to have both a horizontal component and a vertical component. And you will remember that when we're working these types of problems, that when we are looking at angles, we always have to define these angles from the positive x-axis so that our positives and negatives will work out correctly. Now, when I work these problems, I prefer to set them up so that I'm working so that I can very easily see my x component and my y component for all of them. So I'm going to start with the tension in rope number 1, or T1. So the x component of that is going to be T1 times the cosine of 30 degrees, okay? And so if I go ahead and solve that out, that's going to give me 0.866 times T1, okay? Similarly, the y component is going to be T1 times the sine of 30 degrees. And so that is going to give me, where'd that number go? 0.500 times T1, okay? So now I'm going to look at T2. Now again, if I'm looking at defining this angle from the positive x-axis, I have to start from here and go around. So what I really need, get a different color here so you can see that, I have to define the angle from here, so I need to know what that angle is from here to here. Well, if this is 40 degrees from the horizontal, that means 180 minus 40 is going to be 140 for the remaining part of that angle. So the horizontal component of T2 is going to be T2 times the cosine of 140 degrees. And the cosine of 140 degrees is a negative 0.766. Whoops, I said 6 and I wrote a 0, times T2. And then that means that the y component is going to be T2 times the sine of 140 degrees. And the sine of 140 degrees is, where did I write that down at? 0.643 times T2. Okay, so there are my horizontal and vertical components of both of the strings. Now I'm also going to have the component of the weight. I have to break that down into x and y components. And once again, I have to define this angle going straight down from the positive x-axis. So if I start here, 90, 180, 270 is the angle that goes straight down. Okay, so this is going to be 49 newtons times the cosine of 270 degrees. Well, the cosine of 270 degrees is 0. And if you think about it, that's what I expect. If the weight is acting straight down, the horizontal component should be 0. So that makes sense. Okay. Then the y component of that is, probably should have had that in parentheses. The y component is going to be 49 newtons times the sine of 270 degrees, and that's going to give me a negative 49 newtons. Okay, so now that I have that, I know the x and the y components of all 3 of the forces that are acting on it. I know that if the flower pot is not accelerating, the sum of the forces has to be equal to 0. So that means that if I take the x component of the forces, if I take 0.866 times T1 minus 0.766 T2, and I subtracted it because it was a negative sign, that has to add up to 0, okay? I could have added plus 0 over here, but it's got to equal 0. The sum of them has to equal 0. Similarly, the same thing is going to be true over here. I'm going to have 0.500 times T1 plus 0.643 times T2 minus 49 newtons. And that also is going to have to be equal to 0. So now, basically what I've got is I've got 2 equations and 2 unknowns, and I can handle that by solving, just by using some algebra. So if I look at this equation first, if I move this to the other side, I'm going to have 0.866 T1 equals 0.766 times T2. And if I solve for one of those, if I solve for T2 and I divide both sides, if I take 0.866 and divided it by 0.766, that's going to give me 1.13 times T1. Now, I didn't solve anything there, but I do have a relationship between the two of them. I want to do, what I want to do is I want to take this and I'm going to put this relationship in over here. So I'm going to take 0.500 times T1 plus 0.643, but I know T2 is the same as 1.13 times T1. So I'm going to plug this in for this T2 over here. So this is going to be 1.13 times T1 equals, I'm going to move that 49 newtons to the other side so that it's positive. Okay? Now I have one equation and one unknown, so now it's not difficult to solve. So when I crunch all this math, I end up with, if I can put my glasses on so I can see what that is supposed to come out to be. This is 1.226 times T1 equals 49 newtons. So when I divide both sides by 1.226, I end up with T1 having a value of 4.0 times 10 to the first newtons. I need to have two significant figures there. Okay. Then once I know T1, then I can go back and I can plug in 40 newtons right here so I can solve for T2. So I'm going to have 1.13 times 4.0 times 10 to the first newtons equals T2. And again, when you crunch those numbers, T2 will end up being 45 newtons. So there's T2 and there is T1. Okay, now, yes, my whole whiteboard is now full. However, this isn't that different from what we did before. So what you have to keep in mind is, first of all, you're going to draw a big diagram so you can see all of your forces and exactly which direction they're acting. Don't draw a little bitty diagram up in the corner. Use plenty of paper. Make sure your diagram is big enough so you can really see what's going on. Okay, then you want to break down each force into its x and y components using the sines and the cosines of the angles. Make sure that you've identified your angle from the positive x-axis. Okay, don't just use the angle that's written in up there because otherwise you're going to have some goofy positive, they're all going to be positive instead of having correct positive and negative signs, and they won't cancel out. So once you have it broken down into x and y components, the sum of the x components has to be 0. The sum of the y components also has to be 0 because there's no acceleration. Okay, then generally you're going to have two equations, two unknowns, and then you're just going to have to use the techniques that you learned in Algebra 2 to be able to solve for those two unknowns. Okay, so it's a lot of math. The physics really isn't too difficult. Okay, so you'll get some practice dealing with those kinds of problems.